In this video, we are going to take a single example and calculate the bases and dimension of all four fundamental subspaces: the row space, the column space, the null space, and the left null space. As we work through this problem, we're going to need the transpose of the matrix A. So the first thing we're going to do is jot down the transpose for later use. And that transpose is going to look like this. The original matrix A is 3 by 5, 3 rows and 5 columns. So A transpose is going to be 5 by 3. The first row goes into the first column, the second row goes into the second column, and the third row goes into the third column. So we'll set A transpose aside and we'll get to it in a minute. Where are we going to use A and A transpose? Well, we're going to be calculating the column space, the row space, and the null space, that's C, R, and N, using A. We'll use the transpose when we get around to calculating the left null space, which is denoted N of A transpose. There's an alternative method for calculating the column space from A transpose, but we're going to be doing everything mainly with A until we get to the left null space. The first thing that we need to do, like many of our problems in here, is to row reduce our matrix A. So we start with A, and then the first row operation that I'm going to do is going to be to combine rows 1 and row 2 to replace row 2. After doing that, the next sensible thing to do will be to take row 2 minus row 3. After the first row operation, I see that my next two rows look identical to each other. And so after doing row 2 minus row 3, I'm going to get a row of all zeros appearing here. Now at this point, my matrix is in row echelon form. I can actually tell that I'm going to have 2 independent rows and therefore 2 independent columns, but I'm going to do one more row operation to put it into reduced row echelon form, because when I do calculate the null space, it'll make that calculation easier. So the last row operation that I'm going to do is going to be to take minus 3 row 2 plus row 1 into row 1. I'm actually using this entry right here as the pivot with which to get rid of the 3 above it with this last row operation, which converts this entry into a 0. This last step, putting it into true reduced row echelon form, is going to make my life easier. Okay, so I've taken A now and I've put it into reduced row echelon form. We're going to go ahead and do the same thing with A transpose. Working with A transpose is a little bit irritating because we have more rows now to deal with, and so right off the bat I'm going to be doing several row operations all at once. So I'm going to be using my first entry as a pivot, and I'm going to use this pivot to eliminate the entry in row 1, the entry in row 2, and the entry in row 3. So I have 3 simultaneous row operations that I'm going to be doing. This is going to give me immediately a row of zeros, and it's going to change up these 2 rows right here. I need to follow this up with a couple more row operations. So after this, I'm going to be doing minus 2 row 3 plus row 4. That means I'm using this entry as the pivot and getting rid of the 2 underneath it. And I'm also going to be getting rid of the 1 underneath it as well. And that brings me down to this second to last matrix, and I have one more step. That last step is going to be given by combining row 3 and row 1. So when I take row 3 plus row 1 into row 1, that means I am going to be using this minus 1 as the pivot, and I'm going to be eliminating the little 1 that sits above it. And after I do that, I get the reduced row echelon form of both of my matrices. And I'm going to copy them down below because I'd like to do a little bit of highlighting. So let's take the reduced row echelon form of A and the reduced row echelon form of A transpose and look a little bit more closely at them. So let me jot down what these are. Okay, so we have our reduced row echelon form for A here and our reduced row echelon form for A transpose here. All right. Now I want to see which of these rows and columns are independent and which of them are dependent. So let me highlight with green all of the independent columns in A. I have an independent column here and I have an independent column here. Both of these look like standard unit basis vectors in R3. As a matter of fact, you may find it helpful to draw in the staircase when you're trying to figure out where your independent vectors are. The other 3 column vectors are dependent on those 2. So let's use pink and highlight those. Okay. I also have independent rows in rows 1 and rows 2. The row of zeros at the end, this is the dependent row. Independent, independent, dependent, independent, dependent, independent, dependent, dependent. And let me observe as I go along that I have that the number of independent rows is equal to 2, and that has to be equal to the number of independent columns, also 2, and this is all equal to the rank. So the rank is 2. The number of dependent columns for my 3 by 5 matrix is the number of remaining columns, which is 3. This is equal to the nullity, which is the dimension of the null space. And I need to have that the rank plus the nullity is equal to the total number of columns, which is n. So I have here 2 plus 3 is equal to n. Later on, when I write down the basis for the null space, I'm going to want to make sure that I actually have 3 basis vectors there. And I want to make sure that I have 2 basis vectors for the row space and the column space. Let's now do the same thing for AA transpose. I have 3 columns here. 2 of them are independent, and then the third column is clearly a linear combination of the previous 2. In terms of rows, I have 2 independent rows, and then the rest are dependent. So I have an independent row here, I have an independent row here, and then all these rows of zeros are my dependent rows. Okay, and so here, the most important piece of information that I need is the number of dependent columns, because all I need a transpose for, if you remember from right here, is to calculate the left null space. And so here I just want to have the number of dependent columns. And so the dimension of the left null space is equal to the number of dependent columns in A transpose as opposed to in A, and that's going to be equal to 1. And you can also observe here that if I take the left nullity plus the rank, that ought to equal to m, which is the number of rows. N is the number of columns, m is the number of rows in an m by n matrix, and so that's 1 plus 2 equals 3. There's my sanity check. All right, now let's calculate the bases for all of these subspaces. It would be helpful while we do this if we take some of our work with us onto the next page, because we're certainly going to run out of room here. So let's take our calculations for A and copy them onto the next page. Okay, so here's A. We get to see the rows and columns again, and now we're going to write down bases for the row space, the column space, and we'll use this for the left null, for the regular null space as well. Let's do the row space first. Okay. So for the row space, you can actually use either the original matrix or you can use your reduced matrix. In the reduced matrix, your independent rows are here and here. And since we didn't do any row swaps, this corresponds with row 1 and row 2 in the original matrix. Either one of them is a valid set of vectors to use for your basis for your row space, because row operations preserve the row space. So you can use either one when you do that. So we have 2 options. We have 1, 3, 0, minus 5, 3, and 0, 0, 1, 2, 1 coming from here, or we could use the original 2 rows from the original matrix. The dimension is equal to 2 because there are 2 basis vectors spanning the row space, because there are 2 independent rows. Now let's write down a basis for the column space of A. The important thing to keep in mind is that for the column space, we must use the original matrix A. We cannot use the reduced row echelon form, because when you do row operations, you change the column space. So what you do is you find your 2 independent columns, which in our example were columns 1 and columns 3. And then you go back to the original matrix A and you take the corresponding columns, column 1 and column 3. So for the column space, a basis is going to be given by 1, 1, 0 and 3, 2, 1 from the original matrix A. And the dimension is also equal to 2 because there are 1, 2 vectors in this basis, because there are 2 independent columns. These 2 numbers should be the same. If you've done things correctly, then the rank of the matrix is calculated from either one of these, so they better be the same number. By the way, this isn't the only correct answer for the basis for the column space of A. Another way to get a basis for the column space of A is to use AA transpose. So if we went back to our AA transpose, which was here, and we grabbed the two independent rows, 1, 0, 1, and 0, minus 1, 1, those two rows would also make up a basis for the column space. Because remember, in A transpose, columns are rows and rows are columns. So we could have also used those as well. And these two bases are related by a change of basis. I like to use this first method, but if you're working with A transpose, you can also get a basis for the column space from that as well. All right, next we're going to need to write down bases for the null space and the left null space. So let's make a little bit of room on the page. All right. Null space calculations take a little bit more work. So let me write down our matrix again and highlight yet one more time the dependent columns. For every dependent column, these are the ones pictured in pink, we're going to get a basis vector for the null space. The dependent columns give rise to special solutions to the null equation, AX equals 0. And it's those special solutions that are going to form the basis. So I'm going to write down for every dependent column, I'm going to write down a dependency relation and then use that to encode a special vector that's going to make my basis vector. The first column that I'm going to look at is the second column, 3, 0, 0. So what I have here is that 3 times column 1 gives me column 2. And using this, I'm going to rewrite the equation and move this over to the right-hand side. That gives me 0 is equal to minus 3 column 1 plus 1 times column 2. And I'm going to throw in columns 3, 4, and 5 as well with coefficient 0. And then each of those coefficients, minus 3, 1, 0, 0, 0, I'm going to put as the coefficients of this vector S1. This is my first basis vector. It's the coefficients from the dependency relation from the reduced row echelon form of A. And I'm going to repeat this 2 more times for the 2 remaining dependent column vectors. Let me move things around a bit and make space on the page. That way we can continue working here. We'll put our alternative calculation over here, and we'll write down our 2 remaining basis vectors. So for column number 4 and column number 5, I'm going to get 2 more special solutions. I'm calling them S2 and S3. And I'll say a bit more in a second about why I'm calling them special solutions. From the dependency relations, minus 5 column 1 plus 2 column 2 gives me column 3. That's because if I take minus 5 times this column plus 2 times this column, I get this column. And likewise, I get another dependency relation, 3 times the first column minus this column, giving me the last 5th column in my matrix. And like I did before with this one, I'm going to take the coefficients of the equation that's set equal to 0 and then encode them into these basis vectors. So I'm calling them special solutions because when you're dealing with a null space, it needs to be the case that A, S1 is equal to 0. At this point, if you would like to check that your work is correct, you can take your original matrix A, and then you can matrix multiply times the vector, S1 or S2 or S3, and you should get 0. If you've done everything correctly, then this matrix times any of these vectors, S1, S2, or S3, so let's take this one for example, will give us the 0 vector. These should be solutions to the null equation because they're basis vectors for the null space. And if we check this out here, what we're going to get if we do matrix times vector is minus 3 plus a bunch of zeros. So 0. We get a minus 3 plus a bunch of zeros. And then we get a bunch of zeros, 0, 0, 0. So we do indeed get the 0 vector, and it works out. It's a good idea to check your work, so when you're working through an exercise like this, you can check all 3 of them. But these three vectors, S1, S2, and S3, give us our basis for the null space, which is dimension 3 because there are the 3 basis vectors. So our basis we'll write down completely as S1, S2, S3. So here's our basis. Minus 3, 1, 0, 0, 0. 5, minus 2, 1, 0, 0. And minus 3, 1, 0, 0, 1. These are my 3 basis vectors for the null space of A. We have one last thing to do now, and that is to calculate the basis for the left null space. And for that, we're going to use A transpose. So let me go back and grab my A transpose. That was this matrix right here in reduced row echelon form. So I am going to put down this matrix, which I'll remind you is the reduced row echelon form of A transpose, because in here I can easily see the dependent and independent columns. I've got an independent column, and this third one is a dependent column. I only have one dependent column, so I only have one dependency relation to look at. This column 1, 0, 1, 0, 0 is equal to 1, 0, 0, 0, 0 plus a scalar of -1 times the vector 0, 0, -1, 0, 0. This is column 1, this is column 2, and this is column 3. So that's my one and only dependency relation that I have for the reduced row echelon form of A transpose. And I'm going to rewrite this now as 0 is equal to column 1, 1 times column 1, minus 1 times column 2, minus 1 times column 3. And now I'm going to transcribe a vector out of this data. My 1, my -1, and my -1 become the coefficients of the vector 1, -1, -1. And this 1 vector is my 1 basis element. So the dimension of the left null space is equal to 1, and this is the entire basis right here. So there I have it. I have the 4 bases for my 4 fundamental subspaces: the left null space, the null space, the row space, and the column space.